enough energy to jump up here, and I've got to have a state for them to jump up here. So N depends on this so-called density of states. How many states per unit volume do I have? In other words, if we thought of this as the conduction band, how many chairs do I have? I only have 5, so I can't have more than 5 people in them. It's a little bit more complicated than that in the semiconductor, but it's similar to that. So how many vacant states are there? And what's the probability that that state's going to be occupied? Because the transition between here and here is a very statistical process. You have to use equilibrium statistical mechanics to come up with that probability. And that in and of itself, those two terms in and of themselves are very complicated to come up with. But if I knew how many states per unit volume I have and the probability that they're occupied, I could multiply those two functions together, integrate over the conduction band, and that'd give me N. And I could do a similar thing down here. It's very analogous. Do a similar thing to the holes. And that will tell me how many holes I have, how many electrons I have, and then I just plug this in and the velocity is related to the field. So that's the drift component. There's also a diffusion component that if the distribution of electrons and holes are uniform, then great. But if they're non-uniform and I have a gradient, you're going to have a tendency for there to be diffusion from the higher concentration to the lower concentration, and that gives rise to a current. And believe it or not, that component of current is dominant in the way PN junction diodes work. They're basically diffusive devices. They're not drift devices. So you think you're applying a voltage and driving current through that diode. In reality, what's happening is diffusion current. So those concepts put together with lots of derivations, we come up with the following equations for current density. So let me just walk you through what this means. This is for electrons. This is for holes. This is amps per square centimeter, typically. This is the drift component. This is the diffusion component. The drift component will Qn, Qp, that's your flux density, the number of charges per unit volume, and the velocity is given by mu e, where e is a field, and mu is kind of a constant. It's called the mobility, and it's the ease with which you can push charge through a semiconductor. It's kind of like resistance, sort of. But imagine an electron, imagine me moving through a room. I'm trying to get over here and I keep bumping into things. Well, the more things there are to bump into, the harder it is for me to get from here to there. But if there's nothing in between me, I can get there a lot more quickly. Well, this is a measure of how easy it is to move through material. It depends on the material. So that gives you the drift current, the voltage applied to current flows. This is your diffusion component. Notice it's a gradient, dN dx. If n is constant, well, that's 0 and I get no diffusion. But if there's a gradient, I'll get a diffusion current component, and that's the diffusion constant or diffusion coefficient, which just comes out of the equations. So I've got 2 drift terms and 2 diffusion terms, and so the total current in a semiconductor is the sum of all 4 of those terms. So J total is Jn plus Jp. Okay? So you've got lots of terms there, and you basically have, to really solve for that, it's in essence a differential equation. Now just to complete the model, kind of like Maxwell's equations, there are 4 equations that basically describe essentially all of electromagnetic phenomena. There are 5 equations that describe the phenomena in the semiconductor. This gives you the current density component, so that's 2 of them. There are also 3 others, and I'm just going to throw them up so you can see them. One is the Poisson equation. That actually is one of Maxwell's equations, but put in a different form. And basically, Poisson's equation relates rho, which in this case is a charge density. It relates a charge density to electric field. If I have a distribution of charge, if I have a bunch of positive charges here and negative charges here, there's going to be a field there. And so Poisson's equation allows you to calculate the field if I know the charge density. That's just a general statement of Poisson's equation that applies everywhere. In a semiconductor, and that's the free space permittivity and dielectric constant. In a semiconductor, there are 4 sources of charge. There's the holes, which are positive charges. There's the electrons, which are negative charges. And there are these 2 other guys that we're going to talk about next time, but they're the donors and the acceptors. Pure silicon doesn't conduct very well. So I add impurities to it to give it extra electrons or extra holes, and it increases its conductivity to be useful. And this represents those doping concentrations. They're essentially fixed numbers that you can decide on. But they all give rise to all the charge in the semiconductor. The Poisson's equation relates that charge to the induced electric field, if you will. So that's not too surprising, especially when we look at junction devices. There's all kinds of space charge all over the place, and we need to have a field. The other two equations, I'm not going to go into very much, they're very nasty looking, but these are called the electron and hole continuity equations. And they're equations that describe the time evolution of the change in the electron and the hole density as a unit of time as charge flows in and out of a piece of material. You can see that that change depends on the field and the electron concentration and their derivatives, and depends on the diffusion coefficient and the second derivative. And you can see likewise things down here for holes. It also depends on these things. If you look at the outline, I said we were going to talk about generation and recombination, but I was much too ambitious. But are those terms. The idea is that M naught and P naught are the equilibrium concentrations. You've got a device, there's no voltage applied. You have M naught and P naught electrons. You apply a voltage, charge starts moving, and you inject charge in certain regions. And so this is the total electron concentration, the equilibrium concentration, and the difference is the excess. So it's the excess carriers that are induced in a working device, and they're divided by this time constant, which is how long they survive for a lifetime. So modeling a semiconductor is essentially taking those two equations and those three equations and solving them simultaneously and self-consistently because they're all coupled. And so if you really want to solve it, you've got 5 second-order coupled partial differential equations with variable coefficients, which make them nonlinear and almost impossible to solve. Fortunately, for most problems, you don't need all these terms, so you can reduce them to fairly simple models. So in any case, that's the basic model for semiconductor transport. So my concluding remarks are, semiconductor behavior is based on quantum mechanical and quasi-classical models. I didn't really talk too much about this, but when we developed the models I just showed you, we used this, but we classify it a little bit and make it simpler by using quasi-classical models that make things a little bit easier to work with. One major result from all this is the energy band diagram in real space and K-space, which is crucial in understanding how a device works. And we'll do that next time, looking at some diodes and transistors and structures that we use in electronics and how you can understand them from the band diagram. The transport equations describe electrons, E minus, holes, H plus, electron and hole motion due to an applied electric field and a concentration gradient. Next time, we'll talk about how you dope a semiconductor to make it P-type or N-type, so you get a P-N diode. And then we'll look at qualitatively the operation of several classical devices, diodes, transistors, Schottky diodes, based on the band diagrams and the models we've developed. And maybe, if there's time, which there probably won't be, we'll look at some applications in research in this area that's being done and that we're doing in our group. So that concludes my talk today. Sorry I went over a little bit. Does anybody have any questions? I know you're probably tired of listening to me. But, questions? I'll send you guys a copy of these PowerPoints so you can look at them, ask me questions if you have them, and then it'll be easier to follow the next talk I did. By the way, next Tuesday, Dr. Nana will give his grad school presentation. So, questions? Yes.
So I guess in metals of the case when they have partially filled valence bands, do you get interesting relationships for the band above that and below? So do you consider both transitions or?
Not really. It depends on the metal structure.
So I was just wondering, for correlating that to bond strength like you did for silicon, if that was a possibility.
Let's go back to that diagram. The idea with a semiconductor or an insulator is that based on its molecular structure, if you will, all the electrons in the outer shell are inside a covalent bond. So imagine I can put 4 silicon atoms on each of these guys. And so all those electrons are tightly bound. There's no free electrons at all. In a metal, the bonding is different. And there are lots of electrons that are free. For example, like this guy right here is free in this particular case. So in a metal, the idea is you don't have all these electrons in chemical bonds. They're just sitting in the outer valence shell almost free. It doesn't take much energy at all to make them move. So in a metal, you've got chemical bonds, and that's what these guys are, but you also have extra electrons that don't participate in a bond. So they're so weakly bound to the atom that it takes practically no energy, as long as you're well above absolute zero. I mean, you could even be very, very cold temperatures, but as long as you're well above absolute zero, you've already got lots of metal electrons that are moving around in empty space between the atoms. So really, they're already there waiting to move. All you have to do is apply a field and they'll zip by. There's no bond breakage that's necessary. And I don't think, I mean, I suppose you could ionize the metal. I've never really thought about it. You could get some bond breakage, I suppose, and get some extra electrons. But for the most part, that's what's represented here. You've got all these free states, and you've got electrons that can easily move in them because they're not all bound, so you don't need to break a bond. So to get an electron from here to here really would just take increasing the energy, increasing the temperature a lot. And so for most metals, we don't really even worry about that transition. So in some sense, how we define what we call that band and that band, conduction band, valence band, whatever, it's just kind of a buzzword. In a sense, you don't really need to even think about the conduction band of a metal because the outermost band that has any electrons in it at all is only partially filled. So mostly everything moves about in that energy space. So you don't have to worry about bond breakage.
Would that be like melting or something?
If you actually got electrons up here?
Yeah.
Probably not. You could probably get, I don't really know, to tell you the truth, but I don't think that the energy necessary to jump from here to here is enough that it would cause the metal to melt. I would imagine you'd get electrons jumping up here and maybe even up there before you get to the point where you actually start getting melted. And once you get to that point, all bets are kind of off at that point. Then we have to talk to the metallurgist as to what happens. Other questions? Okay, well, I guess that's all we'll do for now, and I think lunch is either on the way or maybe back in the back.